Imagine you are standing on the side of a mountain and you cannot tell. The slope under your boots is so gentle you could almost be walking across a plain. The ground rolls away in every direction to a horizon that sits only about 3 kilometers off, and then it's gone. No peak ahead of you, no drop behind you, nothing that looks like a mountain at all. And yet you are climbing. You have been climbing for days. Because this shallow, rust-colored rise, the one that refuses to look like anything, is the tallest mountain in the solar system. It's called Olympus Mons. It stands on Mars, about 2.5 times the height of Mount Everest, and roughly as wide as the whole country of Italy. It is so vast and so shallow that no one standing on its surface can ever see the entire thing at once. Not from the plains far below, not even from the very top, which makes it a genuinely strange thing to try to climb. Because how do you climb a mountain you can't see? How do you cross something the size of a country, in air so thin the summit pokes up towards space? Under radiation that would be killing you slowly the entire way. The challenge was never steepness, it's distance, and cold, and time, and a planet doing everything it can to stop you from surviving the walk. And yet we've worked it out. In real, careful detail, exactly what it would take to put a single human being on the highest ground in the solar system and bring them back down alive. Let's climb it. Or at least, let's understand what climbing it would really mean. The astronomer was Giovanni Schiaparelli, and the name he gave that pale point was Nix Olympica, Latin for Olympic snow. This was in the late 1800s, and for a long time that was all it was. A name for a bright patch. Just a smudge that stayed bright when the rest of Mars went dark. Here's the thing you have to understand about looking at Mars from Earth back then. You couldn't see the ground. You couldn't see height, or depth, or shape. All you could see was brightness, which patches reflected more light, and which reflected less. Astronomers called these albedo features, and Nix Olympica was one of them. A place that was brighter than its surroundings, for reasons no one could explain. Schiaparelli's real contribution wasn't a measurement, it was an inference. He noticed that during the great dust storms, his bright patches were among the last features anyone could see, and he reasoned they must be standing above the dust. He guessed they were high. That was it, a guess built from almost nothing. And here's what's remarkable. The guess held. In the long years before any spacecraft ever reached Mars, some astronomers came to suspect that this bright feature really might be a mountain, that its stubborn brightness through the dust was telling them something about its height. The idea of a great peak at Nix Olympica was quietly in the air well before anyone had a single close-up image to prove it. Human beings reasoned their way to the tallest mountain in the solar system from a patch of light on a wobbling disk and simply waited to be confirmed. And for decades, that guess just sat there, unconfirmed, waiting. Then, in the year 1971, we sent a spacecraft called Mariner 9 into orbit around Mars. And in one of those coincidences that sounds too perfect to be real, Mariner 9 arrived in the middle of a global dust storm. The entire planet was hidden. The cameras looked down and saw nothing but haze. But as the dust began to settle, a few things started to poke through. The first features to emerge from that planet-wide storm were the summits of enormous volcanoes, rising above the murk exactly the way Schiaparelli had guessed they would. And when we finally got a clear look, one of them turned out to be his bright patch. Nix Olympica wasn't snow at all. It was the peak of a colossal shield volcano. Standing so high, it broke through the weather of an entire world. We gave the volcano a new name to separate it from the old albedo feature. We called it Olympus Mons. A man had inferred a mountain from a smudge of light and been right, and never lived to know it. So how big is it, really? This turns out to be a genuinely difficult question, and the difficulty is part of the story. But let's start with the number most people have heard. Measured by the Mars Orbiter Laser Altimeter, an instrument that fired laser pulses down at the surface and timed how long they took to come back. Olympus Mons stands about 21.25 kilometers high. In the units people usually reach for, that's close to 70,000 feet. About 2.5 times the height of Mount Everest measured from sea level. Now, hold that in your head for a moment, because it doesn't quite capture the thing. Everest is a spike. It's a sharp, dramatic peak that stabs up out of a mountain range, and you can stand in Nepal and look up and see it. All of it, a wall of rock against the sky. Olympus Mons is nothing like that. It is a shield volcano, the same broad, gently sloping shape as the volcanoes that built the Hawaiian Islands, only scaled up to something no place on Earth can match. It is about 600 kilometers wide. That's roughly the size of the country of Italy. Some comparisons reach for France or the state of Arizona. Whichever you pick, the point is the same. This is not a mountain you could photograph. It's a mountain the size of a nation. And here is the fact I want you to sit with for a second. If you were standing on top of Olympus Mons, you would not know you were on a mountain at all. Think about what that means. The slope of this volcano is astonishingly gentle, an average grade of about 5%. Its flanks rising at only 2 to 6 degrees. That's a slope you could comfortably drive up. And because the whole thing is so wide and so shallow, and because Mars is a smaller world with a tighter curve to its surface, the horizon near the summit sits only about 3 kilometers away. The mountain simply falls away past the edge of what you can see. You could stand at the highest point in the entire solar system, turn slowly in a full circle, and see nothing but a flat, reddish plain rolling off to a close horizon in every direction. No sense of height at all, just ground. And it's not only the summit that plays this trick. Because of the volcano's sheer size and those shallow slopes, an observer standing anywhere on the Martian surface, even far out on the plains, even at a great distance, could never take in the whole profile of the mountain at once. The curve of the planet and the bulk of the volcano itself would always hide part of it below the horizon. There is, quite literally, no place you can stand on Mars and see Olympus Mons as a single shape. It is too large to be looked at. The mountain hides from the person standing on it and from the person standing beside it. Remember that. We'll come back to it. Now the obvious question. Why here? Why did Mars, a smaller, colder, quieter planet than ours, build the largest volcano we've ever found, when Earth, with all its fire and motion, never came close? The answer is almost the opposite of what you'd expect. Olympus Mons is so enormous not because Mars is more active than Earth, but because Mars holds still. On Earth, the crust is broken into plates that drift. When a plume of hot rock rises from deep in the planet and punches a volcano through the surface, the plate keeps sliding along, carrying that volcano away from its heat source. Over time, the plume punches through again in a new spot, and again, and again. That's exactly how Hawaii formed, not as one giant mountain, but as a long chain of islands, each one a separate volcano that drifted off the hotspot before it could grow too big. Mars doesn't do that. Mars lacks mobile tectonic plates. Its crust sits fixed over the hotspot below, and it stays there. So instead of building a chain of modest volcanoes, all that molten rock came up in the same place for an unimaginably long time, pouring out over and over onto the exact same ground. One vent, one growing shield, no conveyor belt to carry it away. And Mars gave that process a few more advantages. The planet's gravity is weaker, which means there was less force holding the rising magma down. The magma chambers themselves are thought to be far larger and deeper than the ones beneath Earth's volcanoes. And the lava that erupted was thin and runny basaltic, low in viscosity, so it flowed a long way before it cooled, spreading out into those famously gentle slopes instead of piling up into something steep. The volcano we see is the result of many thousands of these fluid lava flows layered on top of each other over enormous spans of time. Look closely at the flanks and you can still read them. Long channels with raised rims along their edges, where the outer skin of a lava flow cooled and hardened, while a river of molten rock kept running down the middle. There are collapsed lava tubes that show up as chains of pits and broad fans where lava spilled out from tunnels beneath the surface. What Olympus Mons is made of tells the same story. Its surface is roughly 44% silicate rock, with a heavy dose of iron oxides about 17.5%, which is a large part of why Mars looks red at all. There's aluminum, magnesium, and calcium in there, and an unusually high share of sulfur compounds. These are the fingerprints of basalt, the runny volcanic rock that builds shields, not spikes. And all of that weight has to rest on something. Beneath Olympus Mons lies a slab of Martian crust, and upper mantle the lithosphere thought to be around 70 kilometers thick, a rigid raft strong enough to bear a mountain this size without simply crumpling. That strength is part of the recipe. A weaker planet couldn't hold a load like this. Mars can, because Mars is cold and stiff and still. Even so, the mountain is so massive that it is slowly sinking into its own planet. The sheer weight of it presses down on the Martian crust and bends it, creating a shallow, ring-shaped moat around the base, a depression roughly 2 kilometers deep, carved not by erosion, but simply by the burden of the mountain, pushing the world down beneath it. And that sinking isn't even its deeper on the northwestern side than the southeastern side, one of many hints that Olympus Mons is not a tidy, symmetrical dome. In fact, one description of its shape is worth holding on to. The volcano's profile has been likened to a circus tent, but a circus tent held up by a single pole that's been shoved off to one side. The northwestern flank stretches out longer and shallower, sprawling far across the plains. The southeastern side is shorter and steeper. It's lopsided, and the reasons for that lopsidedness reach deep underground, into differences in the ancient sediments the mountain grew on top of. But you don't need the mechanism to feel the strangeness. This is a mountain the size of a country that isn't even the same on both sides. That's the scale we're dealing with. A mountain heavy enough to dent a planet, and wide enough to be lopsided while doing it. Now, let's go to the very top, to the one place on Olympus Mons that actually looks like something happened. At the summit sits a complex of 6 overlapping craters, nested and cutting into one another like a cluster of stacked bowls. These are the calderas, and collectively they're now called the Olympus Paterae. In 2017, the International Astronomical Union gave each of them the name of an Olympian god: Apollo, Zeus, Athena, Hermes, and their companions, the gods, once believed to live on the real Mount Olympus back on Earth. There's a quiet poetry in that. We put the gods on the summit after all, but these craters weren't made by impacts. They were made by collapse. When a magma chamber deep inside the volcano empties out after an eruption, the roof over that empty space has nothing left to hold it up, and it falls in. Each of these 6 calderas is the scar of a separate pulse of volcanic life, a moment when the mountain fed itself, emptied itself, and caved. Using the geometry of the largest of these craters, scientists have estimated that the magma chamber connected to it sat about 32 kilometers below the caldera floor. And these aren't small pits either. Taken together, this summit depression sprawls something like 60 by 80 kilometers across, and drops as much as 3 kilometers down at its deepest. You could lose whole cities in a single one of these collapsed craters. Stand on the floor of the deepest of them, and the walls would rise well over 2 kilometers above you, a hidden canyon carved into the roof of the world, made not by a river, but by a mountain swallowing part of itself. There's one more detail here that quietly connects this faraway summit to us. Scattered on the flanks of Olympus Mons are a couple of impact craters that scientists suspect are among the source regions for a class of Martian meteorites, rocks blasted off Mars by ancient impacts, thrown into space, and eventually caught by Earth. Which means it is at least possible that pieces of this region chips of the largest volcano in the solar system have already fallen to our planet and been picked up and held in human hands long before any human could dream of going the other way. And this is where the mountain starts to feel less like a monument and more like something that might still be breathing. Crater, counting the technique of aging a surface by how many small impacts have peppered, it tells us the calderas formed somewhere between about 350 and 150 million years ago. That already sounds old. But then you look at the lava flows on the flanks, and the numbers get stranger. Some of those flows appear to be 115 million years old. Others look like they're only 2 million years old. On the vast clock of planetary geology, 2 million years ago is essentially this morning. The last confirmed eruption was around 25 million years ago. But the youngest of those flows raises a genuinely open question. The mountain may not be finished, not dead, just very, very quiet, sleeping in long, episodic stretches, the way a fire banks down to embers that could, in principle, catch again. Even the question of how long it took to build this thing is unsettled, and the disagreement is enormous. The total volume of Olympus Mons has been estimated at around 2.5 million cubic kilometers of rock. Now, if it piled up at the same rate Hawaiian volcanoes grow on Earth, you could assemble that entire volume in roughly 25 million years fast, geologically speaking. But others have argued the opposite, that a shield this size, fed by the same deep source over the enormous lifetimes of the Tharsis volcanoes, more likely grew over billions of years. 25 million, or a few billion. That's not a rounding error. That's the difference between a mountain built in a geological instant and one assembled across most of the planet's history, and we still don't know which it is. And I want to plant one small thing here while we're standing on the summit plateau, because it will matter later. If you were up here, really up here, on the highest ground on Mars, walking across the rim of these ancient gods' craters, you still wouldn't feel high. The slope would keep rolling away past a horizon just a few kilometers off. You could be standing on top of the tallest mountain in the solar system and have no way, from your own two eyes, to tell. Keep walking. Let's find the actual highest point, because that too is not where anyone expected it to be. For a long time, if you'd asked where the highest point on Olympus Mons was, the natural answer would have been the caldera, the summit complex, the crown of the volcano. That made sense. That's where the top should be. It's wrong. In a detailed resurvey of the mountain completed in August of 2025, the work of an amateur astronomer and science writer named Jim Singh, working with two collaborators to catalogue the tallest features on the Moon and Mars, the highest point was pinned down precisely, and it isn't on the caldera at all. The single highest stone on Olympus Mons sits on the raised rim of an impact crater called Pangboche, named after a Himalayan village in Nepal. Pangboche is about 11 kilometers across, and its rim, thrown up by the ancient impact that dug it, happens to be the tallest ground on the entire planet. Sit with the irony of that. The highest point in the solar system that we've found on any solid mountain is not the peak of a volcano, it's the lip of a hole. Something fell out of the sky, punched into the flank of the biggest mountain in the solar system, and the debris it kicked up around the edges became the roof of Mars. Run the numbers backward, and you find that without that single impact, the summit right there would sit about 276 meters lower than it does. A random collision, hundreds of millions of years ago, is the reason the highest point stands exactly where it stands. That survey also laid bare something the older measurements had quietly disagreed about for decades: how tall this thing actually is. And the honest answer is that it depends entirely on where you decide the mountain begins. By the laser altimeter, the summit sits about 21,200 meters above the Martian reference level. But measure the drop from the summit down to the average height of the surrounding land, and the mountain's true rise comes out around 22 kilometers. Measure from the very lowest point of its perimeter, and the climb from base to peak can stretch to nearly 24 kilometers. Trace the ground all the way out to the distant plains to the northwest, and the total change in elevation approaches 26. So even the height is contested. Not because anyone is wrong, but because a mountain this large stops having a clean edge. It just fades into the planet. And that fading has a violent side. The whole volcano is ringed by a cliff, a basal escarpment that in places rises as much as 8 to 10 kilometers straight up from the plain. Read that again. The edge of Olympus Mons, the step where it meets the surrounding ground, is in some spots a cliff taller than most mountains on Earth. Nothing else among the Martian shield volcanoes has anything quite like it. And the leading idea for how it formed is almost hard to picture that the flanks of the mountain, over eons, gave way in enormous landslides, sloughing off the edges under their own colossal weight. The evidence for those collapses is spread across the plains around the mountain in rugged, grooved deposits called the aureole vast lobes of broken, corrugated ground that fan out from the base like debris frozen mid-slide. And they, too, are lopsided in exactly the way the mountain is. The aureole reaches much farther to the northwest, one lobe stretching as far as 750 kilometers out than it does to the southeast, the same direction the whole volcano leans. Whatever tore these pieces loose worked harder, or found weaker ground, on the northwestern side. The mountain's collapse, like its shape, has a grain to it. On the eastern edge, researchers have mapped a stretch of the scarp scored by two sets of faults running side by side, one pulling apart at the top, one squeezing together at the bottom, the exact signature you'd expect from a slab of mountain on the verge of sliding. Their models suggest the trigger is water, pressurized fluid trapped in weak layers deep beneath the volcano, lubricating the whole edifice, letting pieces of it creep and eventually break. And the deformation looks young, possibly less than 50 million years old, which raises the same unsettling possibility as the lava flows did. That the mountain is not finished moving. We'll leave the faults there. The pattern repeats all around the volcano, but the point is made. This giant is slowly, quietly tearing at its own edges, because there's a stranger detail waiting near the top, and it involves water but not the kind buried in the rock. For most of the time we've studied Mars, we believed one thing about its equator with real confidence. No frost, the poles. Yes, Mars has vast caps of frozen water and carbon dioxide at the top and bottom of the world. But around the middle of the planet, the mix of sunlight and thin air was thought to keep the surface far too warm for frost to form, even on the highest peaks. It was, as far as anyone could tell, a dry equatorial waste. Then, in 2024, that belief broke. A team led by a young planetary scientist named Adomas Valentinus, doing the work first as a doctoral student, then continuing it as a postdoctoral fellow, found something no one had ever seen near the Martian equator. Patches of water frost sitting in the calderas at the very top of the Tharsis volcanoes, including Olympus Mons. Here's how faint this discovery was. The frost is present for only a few hours after sunrise, and then the sunlight burns it away, and it's gone. It is unbelievably thin, likely only about 1/100th of a millimeter, roughly the width of a single human hair. To find it at all, Valentinus had to sift through more than 30,000 images, filtering them by exactly where and exactly when they were taken, catching that narrow window just after dawn. The frost was spotted with a color camera aboard a European orbiter, then confirmed by 2 other independent instruments. It took years of patience to be sure it was real. And yet, for something so delicate, the scale of what it represents is enormous. The researchers calculated that this thin morning frost involves at least 150,000 tons of water moving between the surface and the atmosphere every single day during the cold seasons, the equivalent of around 60 Olympic swimming pools, cycling up and down over the tallest mountains on the planet every day, and then vanishing before you'd know it had been there. One of the scientists offered a quiet interpretation of what this might mean, that this fleeting frost could be a leftover echo of an ancient climate, a remnant of a time when Mars had precipitation, and maybe even snowfall, drifting down onto these volcanoes. A ghost of weather that ended long ago, still faintly repeating itself at the top of the world every morning. So, picture the summit now, complete. A plain that doesn't feel like a mountain. 6 craters named for gods. The highest stone in the solar system, sitting on the rim of a scar. And across it, for a few hours each cold dawn, a breath of frost, thinner than a hair, made of water that was falling as snow before the dinosaurs. That's the place. Now, could a human being ever stand in it? Let's be careful here, because this is where fact has to be separated cleanly from imagination. No one has climbed Olympus Mons. No crew has landed on Mars at all. What we have instead is a set of detailed studies engineering thought experiments that ask, seriously, what it would take. One of them worked the problem out, step by step, how you would move a human being from a landing site on Mars all the way to the top of the largest mountain in the solar system, and back, alive. It's a concept, not a plan. But it's a rigorous concept, and it tells us something real about the mountain, because to plan the climb, you first have to reckon with everything the mountain would do to you. Start with the air, or rather, the near total lack of it. The average surface pressure on Mars is already only a tiny fraction of Earth's roughly 600 pascals against our 100,000. But at the summit of Olympus Mons, the air thins to around 70 to 80 pascals. That's about 12% of an already impossibly thin Martian atmosphere. For comparison, the pressure at the summit of Mount Everest, the death zone, where climbers can barely breathe, is still around 32,000 pascals. The top of Olympus Mons has so little atmosphere above it that the peak effectively pokes up towards space. There is no version of this where you take off your helmet, not for a second. Then there's the radiation, and this is the quiet danger that never lets up. Mars has no global magnetic field to deflect charged particles, and its atmosphere is too thin to absorb them, so galactic cosmic rays pour down onto the surface more or less unopposed. Mission studies put the effective radiation dose at the surface somewhere around 200 millisieverts per year, several times what you'd absorb on the space station, and detailed modeling shows that a high, exposed place like the top of Olympus Mons is among the worst spots for it, precisely because there's so little air overhead to soak up the particles. And there's a cruel twist buried in that modeling. You might think you could just dig in pile Martian soil over a shelter and hide from the sky. But when cosmic rays slam into that shielding, they shatter and throw off secondary particles, especially neutrons, and those neutrons actually build to a peak a short way underneath the surface, around 30 centimeters down. So a thin layer of shielding can make things worse before it makes them better. To genuinely bring the annual dose down to a level considered relatively safe, you'd need something on the order of 1.5 meters of regolith piled overhead, and on Olympus Mons, with its thin air, you'd need even more of it than you would down in a deep, sheltered crater. The safest places on Mars are the low places. The mountain is the exact opposite of a refuge. So how do you even get to it? Not by climbing in any way a mountaineer would recognize. Remember the slope only about 5%. This is not a wall of ice and rock. There's nothing to grip, nothing to scale. The challenge of Olympus Mons was never steepness, it's distance and exposure and time. The mission concept solved the distance the only sensible way: you drive. The study leaned on a real NASA design, called the Space Exploration Vehicle, a pressurized rover, a small mobile habitat on wheels, so the crew can travel for days without ever putting on a suit. It rolls on 12 wheels that can each pivot a full circle, so it can crawl over rough ground in any direction at a modest pace of around 10 kilometers an hour. Its cabin can keep 2 people alive for about 2 weeks, or a crew of 4 for a single day. Crucially, the astronauts don't step outside to walk the whole way. They'd never survive the exposure. They ride, sealed in, across a slope the size of a country. and the shape of the whole expedition follows from a single, sobering safety rule. The planners built the mission around the distance a stranded astronaut could actually walk back to a pressurized shelter before their suit ran out, a limit of under 10 kilometers. On a mountain hundreds of kilometers wide, that number changes everything. It's why the concept sends not one rover, but two, driving together. If one breaks down beyond repair, the other has to be able to carry the whole crew back to safety. Redundancy isn't a luxury here. On Olympus Mons, a single point of failure is a death sentence, so everything is doubled. The broader mission this study belongs to imagined a crew of 6 reaching Mars and staying on the surface for something like 339 days. Of those 6, 4 would make the journey out to the mountain, and only 2 would actually attempt the final climb, a small, deliberate expedition split off from a larger crew, driving out from a base, chosen for being as close to the volcano as the planners could manage. Everything narrowing, step by step, from a planet to a base, to 2 rovers, to 4 people, to 2, to at the very end 1. Even powering that drive is a problem the mountain shapes. The obvious answer would be solar panels. Every rover we've ever sent to Mars has run on sunlight, but the planners ran the numbers and rejected it. Between the dust that constantly settles on the panels, the storms that can blot out the sun for weeks, the fact that you can only charge in daylight, and the sheer distance involved, solar power simply couldn't guarantee the crew could race back to safety in an emergency. Instead, the study chose fuel cells running on methane, a fuel you can, in principle, make on Mars from its abundant carbon dioxide, trading the simplicity of sunlight for the reliability of something that works in the dark through a storm. And then, at the very end, the concept imposes one rule that turns the whole endeavor back into something human. No vehicle is allowed to fly or drive the final stretch. Above a certain point, the last stretch below the summit, at least one crew member has to get out and cross the final kilometer to the top on foot. Not because the physics demands it, because the meaning does. If you're going to say a person climbed the tallest mountain in the solar system, then at some point a person has to actually walk to the top of it. That last walk would be strange and slow. Mars pulls with only about a third of Earth's gravity, so every step is light, but the suit is heavy with life support and radiation shielding. The air is essentially gone. The cold runs from around 20 degrees above zero down to 150 below, and even at a decent walking pace on Mars, something close to 3.5 kilometers an hour, a suit can only keep you going for a matter of hours before its own supplies run down. A Martian day is a little longer than ours, close to 25 hours, which buys a sliver of extra daylight. But there's no room for wandering. Every meter of that final kilometer would be counted against the clock in your own life support. You'd trudge across an endless, gentle, rust-colored rise, under a sky nearly black even in daylight, toward a horizon that never resolves into a peak. And when you finally reach the highest point, you'd arrive at a plain. To feel the size of this thing properly, you have to hold it against what we already know. Take Everest. Everest works the way a mountain is supposed to work. It is steep, it is sharp, and it announces itself you can stand 100 kilometers away and see it filling the sky. Its summit is a genuine hardship for the human body, an airless spike where people have died just trying to breathe. And yet, measured from sea level, Everest is not even half the height of Olympus Mons. Take Mauna Kea, the Hawaiian volcano that, measured honestly from its base on the ocean floor to its peak, is the tallest mountain on Earth. Olympus Mons beats even that the local rise from the foot of its northwestern cliffs to the summit is a little more than twice the full height of Mauna Kea from the seabed up. There is really only one thing in the catalogue that stands beside it. On the asteroid Vesta, there's a towering central peak inside a crater called Rhea Silvia, and it is roughly the same height. So Olympus Mons isn't cleanly, uncontestedly the tallest, it's approximately tied for the title, which is its own kind of humbling. The 2 tallest mountains we've found are both nothing like the mountains of Earth. and one of them sits on a rock most people have never heard of. But height isn't really the strangeness. The strangeness is everything height usually promises, and this mountain refuses to deliver. A tall mountain on Earth gives you a view. It gives you a peak, an edge, a sense of standing above the world. Olympus Mons gives you none of it. It is so wide that its slope is nearly flat. It is so flat that from its own summit, the horizon sits just 3 kilometers off, and the whole body of the mountain drops away unseen beneath it. Its cliffs are so tall they'd be mountains anywhere else. Its air is so thin the peak reaches toward vacuum. And its true summit isn't even a peak, it's the rim of a hole punched by something falling out of the sky. Every instinct we have about what a mountain is, Olympus Mons quietly breaks. Go back to the beginning. Back to Schiaparelli at his telescope, watching a planet erase itself in a storm, seeing 2 stubborn points of light refuse to go dark, and guessing from nothing, from a smudge that they must be high. He was right. He was more right than he could have imagined. And he never got to see it. He looked at the tallest mountain in the solar system his whole career and only ever saw a bright patch he couldn't explain. But here is the thing that lingers, the thing that ties the whole strange object together. Schiaparelli couldn't see the mountain, and neither could anyone who came after him. Not really. Our spacecraft can measure it to the meter, can map its craters and its cliffs and its frost, and still, no single image ever shows you a mountain because there is no vantage point anywhere from which Olympus Mons looks like one. From orbit, it's too big to be a peak. From the plains, it curves away below the edge of the world. And from the summit, from the highest solid ground we've found anywhere in the solar system, you would turn in a slow circle and see a plane running quietly off to a close horizon, with no way, from your own 2 eyes, to know you were standing on top of anything at all. So imagine you did it. Imagine the drive across a country-sized slope, the last cold kilometer on foot through air that's almost not there, the mountain of shielding you'd need just to survive the sky. Imagine you reached the top. You would have climbed the tallest mountain in the solar system. And you would be standing in a flat, red, silent place that felt like nowhere. The frost would come at dawn and vanish before you were sure you'd seen it. The horizon would sit a few kilometers off, exactly as it does everywhere else. And the mountain, the impossible, planet-denting, storm-piercing mountain, would keep doing the one thing it has always done best. It would refuse to be seen, even by the person standing on its peak. Schiaparelli guessed it was there. We proved him right. And it still hasn't finished hiding from us.